Next, exercise 16. So here we have to find the remainders. The remainder when we divide 7 to the power 1000 by 6 and when we divide 6 to the power 1001 by 7. So you can clearly understand we cannot hope to be able to determine the actual value of 7 to the power 1000 and then divide it by 6 to find the remainder. That is impractical. Instead, we have to use the properties of modular arithmetic. Note that 7 mod 6 is equal to 1 mod 6. Why? Because 7 minus 1 is 6 and that is divisible by 6. So 7 to the power 1000 mod 6 is 1 to the power 1000 mod 6, that is equal to 1 mod 6, and 1 mod 6 is 1 because when we divide an integer by something and the integer is non-negative and less than that divisor, then the integer itself by the structure of the division algorithm becomes the remainder. Next, in the next one the modulus is 7. 6 mod 7 is equal to minus 1 mod 7 because 6 minus minus 1 is 7, which is divisible by 7, so that's why we have this one. Hence 6 to the power 1001 mod 7 is equal to minus 1 to the power 1001 mod 7. 1001 is odd, so we will have minus 1 mod 7, and minus 1 mod 7 is 6 because minus 1 is equal to minus 1 times 7 plus 6, where 6 is non-negative and less than 7, so 6 is the remainder. So this completes the solution. Next exercise, (17). Let A, B, S and T be integers. If A mod St is equal to B mod St, since we are writing modulo St, that means S and T both have to be non-zero integers because we cannot have zero modulus. If this, then show that A mod S is equal to B mod S and A mod T is equal to B mod T. This is one half of the exercise. The second half asks us about a condition on S and T. That will ensure that the converse is also true. That means if instead of the first equation we are given the second and the third equations, then along with that what else do we need to make sure that we will have the first equation as a consequence are needed to make the converse true. Okay, so the first half is actually very easy. Since, or let us just start like this. First we assume A mod ST is equal to B mod ST. Then ST divides A minus B. Since both S and T divide ST, we have S divides A minus B and T also divides A minus B. This implies S mod, A mod S is equal to B mod S. And this implies A mod T is equal to B mod T. So we have proved one half. Now we look for a condition on S and T that will also make the converse true. Next, assume A mod S equal to B mod S, comma A mod T is equal to B mod T, and as an extra condition we are imposing this, that S and T are relatively prime. Then from the first equation we simply get this S divides A minus B. Like that, from the second equation we get T divides A minus B. Now the extra condition will allow us to write the relation that ST also divides A minus B. But how? Unfortunately, I don't remember the number of that exercise. We have already come across an exercise where we had to show that if A divides C, B divides C, and GCD of A and B is 1, then AB also divides C. It's that exercise that we have to use here. Although, because we don't know the number, we will just simply write. We will just simply use it. If you go back to the solved exercises, you will understand which one I am talking about. Since S and T are relatively prime, this implies ST divides A minus B. Hence, A mod ST is equal to B mod ST. and this completes the current solution. Another problem that would need modular arithmetic. This is exercise 18. Eight to the power 402 mod 5. Okay, 8 is congruent to or again I am saying congruent to because Gallian doesn't say anything about congruence, only just remainders. We know that 8 mod 5 is equal to 3 mod 5. However, this will not be a very good simplification, although we do have 3 in place of 8, but still if you raise 3 to the 402th power, that is still unmanageable. So what we can do is we can in such a situation we can look at higher powers of 8, say 8 square. 8 square is 64. How far is 64 from a multiple of 5? Luckily, the next number, the larger number 65 is a multiple of 5. That means 8 square plus 1 is divisible by 5. In other words, 8 square is mod 5 is equal to minus 1 mod 5. Because now the difference is 8 square plus 1, which is 65, but that is divisible by 5. So here we have minus 1. We won't always be this lucky. In some number theoretic calculations, we will have to work with something like this. But then in such cases, what we will do, instead of finding the total power all at once, we will find it in stages. Every time we find something, some power, we divide it by 5, bring it down to the modular value which will be less than 5, and then again raise it to another power. Ultimately we will be able to calculate the power. In this case we are lucky because we now will be able to use this one. So note that 8 square mod 5 is equal to minus 1 mod 5. One more thing we have to keep track of is that the exponent that you are considering in your endeavor to simplify this should somehow give you this. Even if it does not divide, in this case 2 divides 402, so there is no problem. In case it does not divide 402, you can always find a multiple of the exponent that goes close to 402. You get to that stage, then the extra exponent that you need, you just multiply the equation by that power of 8. Okay, so 402 means if we raise everything to the 201th power, then on the left hand side we will have mod 5, on the right hand side mod 5. 201 is odd, so this is minus 1 mod 5, which is nothing but 4. Minus 1 equals minus 1 times 5 plus 4. So this is the remainder. Exercise 19. Show that GCD of A and B, B and C are non-zero integers is 1 if and only if GCD of A and B is 1 and GCD of A and C is also 1. Okay. First, assume that GCD of A and B is 1 and so is GCD of A and C. Then there are integers x, y, u, v such that ax plus by is equal to 1 and ux, oh sorry, what am I writing, au plus cv is also equal to 1. Hence, now what we do, we multiply these two equations. One then is equal to ax plus by times au plus cv. Multiply the terms out. Doing that, we get a square xu plus axcv. Let me write it there. axcv plus byau plus bcyv Okay, so we need A and BC. Now this can be written like this: A times AXU plus XCV plus BYU plus BC times YV. That means we have taken A common out from the first three terms, and in the last term we have BC in the fourth term. So we have been able to express 1 as a linear combination of A and BC with coefficients integers. This is an integer, this YV is also an integer, because A, X, U, C, V, all these things are integers. Thus this is equal to 1. Okay. Conversely, let GCD of A and BC be equal to 1. Okay, so we have to prove that GCD of A and B is also equal to 1 and GCD of B and C is also equal to 1. Then A mu plus BC nu is equal to 1 for some integers mu and nu. Let D be the GCD of A and B. That means D is the greatest common divisor of A and B. Since D is a common divisor of A and B, so D divides both A and B. Since D divides A and D divides B, we have D divides A mu plus BC nu, because D is dividing the first term because it divides A, and D is dividing the second term because it divides B, and this is equal to 1. Now D is a positive integer that divides 1, so D has to be equal to 1, since by definition D is greater than or equal to 1. This implies D is equal to 1, that is this. One can similarly prove that GCD of A and C is equal to 1. Okay, you can use the same equation, and instead of working with GCD of A and B, you work with GCD of A and C. The arguments are the same. So this completes the current solution. Okay, so now leaving the world of GCD, in the next exercise we will look at prime numbers. Let P1, P2, etc. Pn this be distinct positive primes. Show that none of them, they have phrased it not like this. Show that this number P1 times P2 times P3 etc. up to Pn plus 1 is divisible by none of these primes. suppose, to the contrary of what we have been asked to prove, we will suppose the exact opposite. We will suppose that one of the primes divides this given number and then arrive at a contradiction. Suppose pi divides this number for some I lying between 1 and n. Since pi also divides this number, this product of the primes, because pi appears as a factor in this product, so pi will divide this product. We have pi dividing this minus this. Because pi divides this number according to our supposition, and pi already divides this number, which is true, so it will divide their difference. But that difference is actually equal to 1. This is a contradiction. Since pi is greater than 1, every prime is greater than 1, so it cannot divide 1. So our supposition is wrong. That is, none of the given primes can divide the given number, given integer. Okay, I need some more ink. The next exercise naturally would be to show that there are infinitely many primes. Prove that there are infinitely many primes. And there is a hint. I am not writing that hint. They have asked us to use the previous exercise, which anyway we are going to do. This whole proof that there are infinitely many primes consisting of the first exercise solution here, I mean the 20th one and the 21st one, actually is due to Euclid. Euclid proved that there are infinitely many primes in this way. Suppose, so this is Euclid's proof. Suppose that there are only finitely many distinct primes. P1, P2, etc. up to Pn. We consider the integer this n, which is the number we considered in the previous exercise. Okay, now look at this number n. Infinitely many distinct primes means we are considering positive primes. Okay, negative primes we are not considering in this context. So all these are positive primes. So that means the product is a positive integer. That one plus 1 is again a positive integer, that is greater than 1, since n is a positive integer greater than 1, the fundamental theorem of arithmetic implies that n has a prime divisor q. Say n must have a prime divisor since n is greater than 1. Let that prime divisor be q. There may be other prime divisors also, but we need at least one will be there. But according to our supposition, here we have supposed that these are the only available primes. So this q must be one of them. Our forces us to conclude that q is equal to pi for some I. But that in itself contradicts the previous exercise, because the previous exercise says that whatever prime factor this number has, n has, it will not be one of these primes. It will be something else. But this contradicts the so our supposition is wrong. That is, there must be infinitely many primes. This is a remarkable proof by Euclid using the method of contradiction. It shows logically that there must be infinitely many primes. A finite list of primes is not enough to create all the positive integers, because by the fundamental theorem of arithmetic, prime numbers are the building blocks of the positive integers, in the sense that multiplying them we can create all positive integers. However, if this proof shows that a finite list of primes is not enough to create all positive integers. There, if we start with a finite list, then some positive integers like this one, particularly this one, we will find none of its prime factors among that list. Okay. Now next, Okay, we are abruptly jumping from topic to topic. That is because this is a this exercise